second speaker. The second speaker of this conference today is Stephanie van Willigenburg, and she's going to tell us about Schur functions in non-commuting variables. Let's welcome the speaker.
Thank you very much, and thank you to the organizers for organizing this wonderful conference. I've enjoyed all of the talks so far, and I know I'm going to look forward to and enjoy all of the remaining ones as well. And so, welcome. I'm talking to you from beautiful Vancouver in British Columbia, Canada, and thank you very much for coming to listen to my talk today. So this is research that I've done with Farid Alanir-Ifad and Xu Xiao Li. Now, actually, both Farid and Xu Xiao are in the audience. And so if you have any questions during the talk, just pop it into the chat. And what they're going to do is they're actually going to answer your questions in real time. So hopefully this will give you an opportunity to ask questions as soon as they come up, and they'll be able to answer them for you. So without further ado, let's get cracking. So remember that an integer partition lambda, which consists of lambda1 greater than or equal to lambda2 greater than or equal to lambda3 and so on of n, is a list of positive integers whose sum is n. So for example, 3, 2, 2, 1. So you've got 3 greater than or equal to 2, that's equal to 2, that's greater than 1. Well, those numbers add up to 8, and so this is a perfectly nice partition of 8. And so if we're given some partition lambda, then we say that lambda factorial is just going to be equal to lambda 1 factorial, lambda 2 factorial, lambda 3 factorial, and so on. So if we take our newfound friend lambda equal to 3, 2, 2, 1, then lambda factorial is going to be equal to 3 factorial times 2 factorial times 2 factorial times 1 factorial, which is going to be 6 times 2 times 2 times 1, which is 24. Now we can also write our partitions as 1 to the number of 1s we can see, 2 to the number of 2s we can see, 3 to the number of 3s we can see, and so on. And if we write lambda in this sort of notation, then we say lambda to the factorial is going to be the number of 1s we see factorial times the number of 2s we see factorial times the number of 3s we see factorial, and so on. So if we take our running example lambda, well, this is 1 to the 1, 2 to the 2, 3 to the 1. So when we do lambda to the factorial, then this is going to be 1 factorial times 2 factorial times 1 factorial, which is going to be 2. And out of interest, just to check my mouse is working, what number am I circling? Everyone's like, I have no idea what she's circling. What is she talking about? 24, brilliant, thank you, Hannah. Okay, so now that we know that all the equipment's working, let's get on to looking at symmetric functions in non-commuting variables. And for this, we're going to need set partitions. So we say a set partition of the numbers 1 up to n is going to be a partitioning of the numbers 1 up to n into disjoint sets called blocks, such that no block is empty, and when you take the union of all the blocks, you get the numbers 1 up to n again. So if we have a look at an example, notice that this thing here is a perfectly nice set partition of the numbers 1 up to 8, because notice that none of the sets are empty, and when we look, we get the numbers 1, 2, 3, 4, 5, 6, 7, 8. Now, this notation is a little cumbersome, and so what we're going to do is we're simply going to drop the curly braces, we're going to drop the commas, and instead just write our set partitions as 1, 3, 4, 2, 5, 6, 7, 8. And so with this in mind, we can actually calculate the partition determined by our set partition pi. All you do is write down the number of elements in the first block, write down the number of elements in the second block, and so on, and then write these sizes in weakly decreasing order. And we can also let permutations act on our set partitions. All we're going to do is we're going to see where our permutation maps the first block, see where it maps the second block, see where it maps the third block, and so on. So let's do an example. So if we take our set partition 1, 3, 4, 2, 5, 6, 7, 8, then when we make the partition that is determined by the set partition, well, we just look at the sizes of the blocks and we write them in weakly decreasing order. So we're going to have 3, 2, 2, 1. And now if we let this permutation right here act on our set partition, and notice this permutation has been written in one line notation. So 1 goes to 1, 2 goes to 4, 3 goes to 3, 4 goes to 2, 5 goes to 5, 6 goes to 8, 7 goes to 7, and 8 goes to 6, then we're going to get the following thing. So notice that what I'm going to do is I'm going to take where 1 gets mapped to, which is 1, I write it down. See where 3 gets mapped to, it's 3, write it down. See where 4 gets mapped to, it's 2, write it down. Then I'm going to see where 2 gets mapped to, which is 4, write it down. 5 gets mapped to, which is 5, write it down. Then I'm going to see where 6 gets mapped to, which is 8, write it down. Then I'm going to see where 7 gets mapped to, which is 7, write it down. And then where 8 gets mapped to, which is 6, write it down. And then I'm just going to tidy up my set partition to get 1, 2, 3, 4, 5, 6, 7, 8. And now what I'm going to do is I'm going to ramp it up a little. So if I have a set of integers, s, then we say that s plus n is I'm going to take all of my elements of my set S and I'm just going to add n to them. And so with this in mind, for any set partition pi and then another set partition sigma, their slash product pi slash sigma is simply going to be, well, the first thing I'm going to do is I'm just going to write down pi as it is. And then I'm going to take the first block of sigma and I'm going to add n to all of its elements, write it down. Then I'm going to do the same thing with the second block of sigma, third block of sigma, and so on. So let's do an example. So if pi is 1, 3, 4, 2, 5, and sigma is 1, 2, 3, then pi slash sigma is going to be the following thing. We're going to first of all write down 1, 3, 4, 2, 5, and then since this is a set partition of 5, we're then going to write down 1 plus 5, which is 6, 2 plus 5, which is 7, and then 3 plus 5, which is 8. And so now we're in a great position to define the algebra of symmetric functions in non-commuting variables, and this was introduced by Rosas and Sagan in 2004. And there's Mercedes Rosas right there, and there's Bruce Sagan right there. And we're going to define this in terms of some well-known bases, and it should be noted that actually this basis E that we're going to be coming to was actually defined by Wolff, and she defined it back in 1936 when she was actually discovering a non-commuting version of the fundamental theorem of symmetric functions. So let's have a look at some of these bases. So the first one is going to be the monomial symmetric function in non-commuting variables. Now for this, what we're going to take is we're going to take a sum of monomials such that the variable in the jth position is equal to the variable in the kth position if and only if j and k are in the same block. So let's do an example. Say I want to compute M132. Then since 1 and 3 are in the same block, we need our variables in the first and the third position to be identical. And then we're going to have that the variable in the second position has got to be something different. So we're going to get monomials of the form x1, x2, x1, x2, x1, x2, x1, x3, x1, x2, x3, x2, and so on. So that's our first basis. The next basis we're going to look at is going to be the power sum symmetric functions in non-commuting variables. And so here again, we're going to get a sum of monomials where we're going to have the variable in the jth position is equal to the variable in the kth position if j and k are in the same block. So if we wanted to compute P132, well, since 1 and 3 are in the same block, we know that the variables in the first position and the third position have to be identical. So we're going to get monomials of the form x1, x2, x1, x2, x1, x2, and of course, all three of our variables can be identical. That's allowed now. So we are going to have terms like x1 cubed, x2 cubed, and so on. Now we're going to go on to our third basis. So these are going to be the elementary symmetric functions in non-commuting variables. And again, we're going to be looking at a sum of monomials. But now what we're going to do is we're going to have that the variable in the jth position has to be different from the variable in the kth position if j and k are in the same block. So for example, if I wanted to compute E132, then since 1 and 3 are in the same block, we know that our variables in the first and the third position have to be different. So we've got that we can have terms like x1, x1, x2, x1, x2, 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 x1, x2, x1, x1, and of course, all your variables can be different. That is definitely allowed. So you can have monomials such as x1, x2, x3. Then the last of the bases that we're going to look at for the moment is going to be the complete homogeneous symmetric functions in non-commuting variables. Now, these are a little bit more complicated than the other bases we've looked at. So what we're going to do is we're going to express these in terms of our monomial symmetric functions in non-commuting variables that we saw right at the start, along with a coefficient. So how do we compute this coefficient? Well, the first thing you need to do is, well, if you've got sigma and you've got pi, then what you need to do is you need to find their intersection. And this is going to be the maximal set partition, where every block is both a subblock of sigma and a subblock of pi. So probably the best thing to do is to do an example. So let's say we want to compute the complete homogeneous symmetric function in non-commuting variables h132. And say we wanted to compute the coefficient of m123. Well, the first thing we need to do is we need to find the intersection of 123 and 132. And this happens to be 132 because notice that 13 is a subblock of 123 and 13 is a subblock of 13, and then 2 is a subblock of 123 and 2 is a subblock of 2, and you can't find anything bigger than that. So now we've computed this, what we're going to do is we're going to look at the block sizes and take their factorials. So this has two numbers in, so we're going to get 2 factorial. This has one thing in, we're going to get 1 factorial. So 2 factorial times 1 factorial is 2. Now we've done all of that, we're now ready to write down our coefficient. So we're going to get 2m123. And we get exactly the same calculation when we try and find the coefficient of m132. So that's those coefficients. Say on the other hand, we want to compute the coefficient of m123. Well, now we have to look at the intersection of 123 and 132. Well, this turns out to be 1, 2, 3, because 1 is a subblock of 1, 2, and 1 is a subblock of 1, 3. 2 is a subblock of 1, 2, and 2 is a subblock of just 2, and then 3 is a subblock of 3, and 3 is a subblock of 1, 3. Next thing we have to do is we need to look at the sizes of those blocks. So this is going to give us 1 factorial times 1 factorial times 1 factorial, which gives us 1, and thus gives us a coefficient of 1 in front of m123. And then a similar calculation also holds to give us the coefficients of m123 and m123. Okay, so now we have some of our key bases. Let's have a look at a couple of facts. So the first fact is that if pi is a set partition and delta is some sort of permutation, then if we let delta act on m pi, then what we get is m delta of pi that we defined earlier. And then for any basis b, where this can be the power sums, the elementaries, or the complete homogeneous symmetric functions in non-commuting variables, we have that delta acting on b pi is just b delta of pi. And we have a really nice product formula. We have that b pi times b sigma is equal to b pi slash sigma, where this was the slash product we saw earlier. So let's have a look at a couple of examples. So we have that if we have 132 acting on m123, well, this is in one line notation, and it just tells us we switch the 2 and the 3. So we look at this subscript right here, and we just switch the 2 and the 3, giving us m132. And then say we want to multiply together two of our power sums, then p132 times p1 is going to be, by this definition right here, p132 slash 1, which means that all we do is we write this one down again, 132, and then we add 3 to this to get 4. So why did Rosas and Sagan give the names they did to their functions? Well, it's all because of what happens when we let our variables commute. So this is the map called rho. And so if we take our monomial symmetric functions in non-commuting variables and let the variables commute, then you get the classical monomial symmetric functions along with a coefficient. Similarly, if you take your power sum symmetric functions in non-commuting variables and let the variables commute, you get the classical power sum symmetric functions. If you take your elementary symmetric functions in non-commuting variables and let the variables commute, you get your classical elementary symmetric functions along with a coefficient. And similarly, if you take your complete homogeneous symmetric functions in non-commuting variables at the variables commute, you get the classical complete homogeneous symmetric functions along with a coefficient. So if you know what these things are, that's awesome. If not, then you can use these as a definition. But the natural question is where is the Schur functions, right? That's our classical symmetric function that hasn't shown up yet. So what we're going to do is, since these are going to be the crux of our talk, we're going to actually fully directly define Schur functions. So given your favorite partition, the diagram of it is going to be the array of boxes with lambda I boxes in row I from the top. And this is going to be in English notation because I'm in Vancouver, British Columbia. Also, it works really well. So what we're going to have is, say I want to make the diagram of 3, 2, 2, 1. I'm going to have 3 boxes, then 2 boxes, then 2 boxes, then 1. And then I'm going to neatly left justify them. Then a semi-standard Young tableau of shape lambda is going to be a filling of those boxes with the numbers 1, 2, 3, and so on. So the rows weakly increase as we read them from left to right, and the columns strictly increase as we read them from top to bottom. So here's a little example right here. Notice our rows weakly increase, 1, 1, and our columns strictly increase, 1, 2, and then there's just 1 here. And then given a semi-standard Young tableau, we can associate a monomial with it. We're just going to have x1 to the number of 1s we can see, x2 to the number of 2s we can see, and so on. So if we look at this little tableau right here, then the monomial is going to be x1 squared, x2. And then with this in mind, our Schur function S lambda is just, well, take all of your semi-standard Young tableau of shape lambda, take the monomial corresponding to it, and add them all up. So say I wanted to compute S21, then, well, I'm going to make all of my semi-standard Young tableau of shape 2, 1. Here are all the ones that have the numbers 1, 2, and 3. And then I'm going to make the monomials corresponding to them and add them all up. So this one here is going to give me x1 squared x2. This one here is going to give me x1 x2 squared. And then if I move all the way along to the right-hand side, this one will give me x1, x2, x3, and this one also will give me x1, x2, x3, giving me a multiplicity of 2 x1, x2, x3, just as we saw in Jiangsu's talk yesterday. Okay, so now we're going to try and generalize this. So what we're going to do is we're going to introduce dotted Young tableau. So again, this is going to be a filling of your diagrams with the numbers 1, 2, 3, and so on. So our rows weakly increase left to right and our columns strictly increase top to bottom. And in addition, what you're going to do is you're going to throw on 1 dot, 2 dot, 3 dot, 4 dot into your boxes until you're done. And all your boxes have some number of dots in them. But the number of dots you place have got to appear once and only once. So here's a diagram right here. So notice that again, we've got our rows weakly increasing. We've got 1, 1, our columns strictly increasing 1, 2. And notice that I placed 1 dot, 2 dot, 3 dot, done. So then given a dotted Young tableau, we can associate a monomial to it in the following way. We're going to have that xi is in position j if and only if I has j dots above it. So let's look at our example right here. So we've got that 1 has 1 dot above it, so I'm going to write down x1 in the first position. Then we have 2 has 2 dots above it, so I'm going to write down x2 in the second position. And then I have 1 has 3 dots above it, so I'm going to write down x1 in position 3. Then we're going to have that the Rosa-Sagan-Schur functions are going to be defined as follows. So S lambda is going to be, you're going to take all dotted Young tableau of shape lambda, you're going to make the monomial corresponding to it, and then you're going to add them all up. So say I want to compute my Rosa-Sagan-Schur function, S21. Well, I'm going to make all my dotted Young tableau of shape 2, 1, and here are all of the ones that have 2 1s and 1 2. And then I'm going to make the monomials corresponding to it. So here I'm going to get x1, x1, x2. Here I'm also going to give me x1, x1, x2, giving me 2 x1, x1, x2. Then here I'm going to get x1, x2, x1. Here I'm also going to get x1, x2, x1, giving me 2 x1, x2, x1. And then finally I'm going to get x2, x1, x1. Here I'm also going to get x2, x1, x1, again giving me 2 x2, x1, x1, and so on. Then Rosas and Sagan were able to show that the Rosa-Sagan-Schur functions are linearly independent, and when you let the variables commute, then what you get is the classical Schur functions along with a coefficient. However, notice that unfortunately, unlike the other functions we've looked at, they are not a basis for our symmetric functions in non-commuting variables because we only have one for each integer partition, not one for each set partition. So in their 2004 paper, at the end, they asked, is there a way to define functions for set partitions having properties analogous to the ordinary Schur functions? Now, if the answer to the question is no, then, well, we're definitely back on time because that's the end of the talk. However, the answer is yes, there is. And that's what I'm going to be talking about next. And so this is the work that I did with Farid and Xu Xiao. And in fact, this paper was published just 2 weeks ago in Advances in Mathematics. So if you want to read more, then please, I can give you the paper later. Okay, so what we're going to need to do is we're going to need to revisit our Schur functions, and we're going to look at a different definition, not the one involving Tableau. So recall the Jacobi-Trudy identity, which says that S lambda is equal to, well, we're going to make ourselves a matrix where this is the complete homogeneous symmetric function indexed by lambda I minus I plus j, and then we're going to take the determinant of that. And if you get out h0, that's just going to be equal to 1. And if you get out any negative index right here, you're just going to put in a 0 instead. So let's have a look at a quick example. Say I want to complete S21. Well, first of all, I'm going to make this matrix right here, H2, H3, H0, H1. Then I'm going to take the determinant. So I'm going to have H2 times H1 minus H3 times H0. And don't forget that the complete homogeneous symmetric functions are multiplicative. So H2 times H1 is simply H21. And we've got that H3 times H0, well, that's just H3 times 1. And so therefore we're going to get H21 minus H3. So at this point, what we're going to need to do is we're going to take that definition and we're going to generalize it. And for that, what we're going to need is we're going to need our old friend, the Leibniz formula, and this is Leibniz's house right here, but that's not Leibniz, and we're going to make a non-commuting version. So how are we going to do that? Well, we're going to do this by, first of all, when we take our matrix, those entries inside are going to be non-commuting. And then when we actually do our determinant, we're always going to take the product of the entries from the top row to the bottom row. And so with this in mind, the source Schur function, S lambda, is going to be defined as follows. What we're going to do is we're going to take the matrix with our homogeneous, complete homogeneous symmetric function in non-commuting variables whose indices are, well, it's going to be the set partition consisting of one block, 1 up to lambda I minus I plus j, along with a coefficient, and then we're going to take this non-commutative determinant. And again, h0 is going to be 1, and if we ever get a negative number here, we're just going to set this whole thing to 0. Okay, so say I want to compute my source Schur function S21. Well, then I'm going to get this matrix right here. So 1 over 2 factorial h12, 1 over 3 factorial h123, 1 over 0 factorial h empty, and 1 over 1 factorial h1. And now we're going to take its non-commutative determinant. So what we're going to do is we're going to get 1 over 2 factorial h12 times 1 over 1 factorial h1 minus 1 over 3 factorial h123 times 1 over 0 factorial h empty. And we know from our product formula earlier that this is going to be, well, just a half h12 slash 1, which is a half h123, minus a sixth h123. Now, that's all well and good, but we're still only dealing with partitions. Now we need to create a set partition from an integer partition. And we're going to do this using Tableau. And if we've got our set partition pi and our integer partition lambda, then our Tableau tpi is going to be of shape lambda, subject to the following rules. Every element 1, 2, up to n appears exactly once. Rows must increase as we read them from left to right. And if you have rows of the same length, then the first column entries have to increase top to bottom. So we've got an example right here. So notice that we have the numbers 1, 2, 3, 4, 5, 6, 7, 8 appearing once and only once. Our rows are increasing as we read them left to right. And notice that here we have 2 rows with the same length, which is 2. And notice that these first elements, they're increasing. We've got 2, then a 7. And then the correspondence from then on is dead easy. You just read things by row, and those are going to be your blocks. So from tpi, we're going to get the set partition 1, 3, 4, 2, 5, 7, 8, 6. And so with this in mind, we're now going to create a permutation. So what we're going to do is we're going to take this t pi and we're just going to read off the entries from the top row to the bottom row, and that's going to give us our permutation in one line notation. So in this case, we're going to get 1, 3, 4, 2, 5, 7, 8, 6. And so in this way, we know from the last slide that our t pi was associated with a set partition. Now we've got our t pi is associated with a permutation, and so we've got that our set partitions are now associated to a permutation. And then with this in mind, the Schur function in non-commuting variables is going to be defined as follows. We say that S pi is going to be equal to delta pi, which was a thing we made on the previous slide. And then we're going to have that act on our source Schur function, which we had on the slide before that. And that's it. So again, this is best seen through an example. So if pi is our set partition 1, 3, 2, then notice that these blocks become the rows of our tableau. So we get 1, 3, 2. Then we just read the entries by row to get our permutation, 1, 3, 2. And consequently, our Schur function in non-commuting variables, S132, is, well, we take 1, 3, 2, and we have it act on the source Schur function of this shape, which is 2, 1. Well, we computed this on an earlier slide. That's just this expression right here. So now all we need to do is we need to have 1, 3, 2 act on it. Well, all this does is it switches the numbers in the index 2 and 3. And so consequently, we have 2 and 3 get swapped, giving us a half H132. And here 2 and 3 get swapped. That doesn't do anything. So we get minus a sixth H123. Then the really nice thing is that our Schur functions in non-commuting variables form a basis. And if you let the variables commute, then what you get out are the classical Schur functions. And even better is that our source Schur functions naturally refine Rosas and Sagan Schur functions. But unlike the other bases, we don't have that if delta acts on S pi, we get S delta of pi. Happens sometimes, but not always. Now you might think this is a bad thing, but in fact it turns out to be amazingly cool because that means that for every single permutation delta, if you let it act on our Schur functions in non-commuting variables, you get a different basis. So you find yourself with n factorial different bases, every single one of which, when you let the variables commute, they go to the Schur functions. Now I'm going to tell you about another basis, and it's going to have something cool about it too. And for this, we need Young tableau. And we say a Young tableau of shape lambda is a filling of your diagrams with the numbers 1, 2, 3, and so on, such that each number appears exactly once. And so what we're going to do is we're going to do the same trick that we did earlier, which is we're going to associate a permutation with it. We're just going to take our tableau, read the entries by row, and that'll give me a permutation in one line notation. So we'll do an example in a second, but the final thing we need to remember is we're now going to find a new function st, which is just going to be this permutation delta t acting on the appropriate source Schur function. Okay, time for an example. So let us take this Young tableau right here, 2, 1, 3. Then reading by row, that's going to give me a permutation, 2, 1, 3. And so now if I want to make my function st, then by this definition right here, I'm going to have the permutation 2, 1, 3 act on, well, the source Schur function of this shape, which is going to be S2, 1. Okay. Well, we know what this thing is. We calculated it a few slides ago. It's going to be this thing right here. Now we're going to let this permutation act on this, and this permutation just swaps the numbers 1 and 2. Okay, so let's swap the numbers 1 and 2 here. Nothing happens. So again, we get a half 1 H1, 2, 3. And here, if we swap 1 and 2, nothing happens. So again, we'll get minus a sixth H1, 2, 3. And now what we're going to do with our little tableau is we're going to make a row equivalence class. And that row equivalence class is going to consist of all young tableau that have the same shape as T and the same set of row entries as T. But they could be and they will be permuted amongst each other. So let's look at an example. So if this is our favorite little tableau here, then if we want to look at its row equivalence class, then, well, it's going to contain itself, and then the only thing that you can do in order to have the same set of row entries is switch this 1 and 2, which is going to give us this tableau right here. And then, because it's going to be useful on the next slide, we're going to also at this point calculate the associated permutation, which remember is just read by rows. So what I'm going to get for this one is going to be 2, 1, 3. And then for this one, I'm going to get 1, 2, 3. Done. And so now at this point, I'm going to define the tabloid Schur function. And so the tabloid Schur function ST is going to be a sum of those ST tildes, where what's T tilde? Well, it's going to be the sum over all things that are row equivalent to T. So again, let's have a look at an example. So if I want to make the tabloid Schur function of this thing right here, well, we know from the previous slide that by our definition of ST, this is going to consist of a sum that's going to have two terms in it. One of them is going to be 2 on 3 acting on the appropriate source Schur function, and one of them is going to be 1, 2, 3 acting on the appropriate source Schur function. Well, we calculated these on earlier slides as well, so let's just plug that in. So remember that when we calculated this, we got out a half h123 minus a sixth h123, and when we did that with this function as well, we also got a half h123 minus a sixth h123. So adding these together, we're going to get h123, and adding these together, we're going to get minus a third h123. And so with this in mind, it turns out that the tabloid Schur functions also give us a basis, where in particular, the young tableau we pick are the ones that are corresponding to our set partitions using that correspondence we had earlier. And moreover, if we let the variables commute, then what we end up getting is we get back the classical Schur functions along with a coefficient. And then the cool thing about this particular basis is that it is related to representation theory. So given any one of our little young tableau T, we define ET to be the following thing. Going to take a permutation, delta, multiply it by its sign, add them all up, and then have that act on the row equivalence class. Meanwhile, bold E of T is going to be, well, we're going to take those same permutations delta, multiply it by a sign, add them all up, and then have it act on our tabloid Schur function. And what are these deltas? Well, they're going to be all the column stabilizers of T that permute the elements of our tableau within each column. Then, with this in mind, recall that we can define the spect module to be the span of all ETs, and we also have a submodule of the algebra of symmetric function of non-commuting variables, which are going to be spanned by our bold ETs. And the thing that's really cool is that these two modules are isomorphic, and the isomorphism couldn't get much nicer. We just send ET to bold ET, and that's it. Now, while we all love Schur functions, what's even more exciting is going to be skew Schur functions. So let's have a quick look at that. So, given two partitions lambda and mu, the skew diagram lambda skew mu is going to be the array of boxes that are contained in mu but not in lambda. So say I wanted to make 5, 3, 3, 2, skew 2, 2, 1, then I'm going to draw 5, 3, 3, 2. I'm going to locate 2, 2, 1 in the top corner, and then I'm just going to cut it out. And we say that a skew shape is a ribbon if it does not contain any 2x2 subdiagram. And in this case, then we can denote our ribbon just by its row length read from top to bottom. So in this case, we're going to get 3, 1, 2, 2, and that'll be useful later. But now let's go back and have a look at our classical definition of Schur functions. So we say the Schur function, the classical one, is simply going to be, well, S lambda skew mu, which is going to be, we're going to take our complete homogeneous symmetric functions, the classical ones, indexed by lambda I minus mu j minus I plus j. Once you've made that matrix, you're going to take the determinant. Now you can also define it in terms of tableau. You're just going to take a semi-standard Young tableau, but now of shape lambda skew mu, make the monomials corresponding to it, and add them all up. And well, if you've got your Schur function S lambda skew mu, then we can write it as a sum of Schur functions S mu with some coefficients, and these coefficients are the well-known Littlewood-Richardson coefficients. And just one bit of notation, if our skew diagram happens to be a ribbon, then quite often what we'll do is, instead of calling it a Schur function, we'll call it a ribbon Schur function, and we'll denote it by our alpha, where alpha is just the row lengths. So with this in mind, we can define Schur functions in non-commuting variables, and we're going to do it as follows. The first thing we're going to do is we're going to define the source Schur function to be, well, S lambda skew mu is going to be, we're first of all going to take our complete homogeneous symmetric functions in non-commuting variables whose index is going to be 1 up to lambda I minus mu j minus I plus j along with a suitable coefficient, and then we're going to take our non-commutative determinant. And then once we have that, our Schur function in non-commuting variables is going to be indexed by a permutation delta and a shape lambda skew mu, and all we're going to do is we're going to let that permutation delta act on our suitable source Schur function. And then the cool thing is that if you let the variables commute, then what you get back is just the classical Schur functions. So let's have a quick look at an example. So say I wanted to compute the source Schur function S22 skew 1. So the first thing we're going to do is we're going to make our matrix. That's this thing right here. Then I've got to take my non-commutative determinant, which is going to be 1 over 1 factorial h1 times 1 over 2 factorial h12 minus 1 over 3 factorial h123 times 1 over 0 factorial h empty. So by our product rule right from the start of the talk, that's going to be a half h1/12, which is just a half h123. And then it's going to be minus a sixth h123, which just stays as it is. So then if I want to make my Schur function in non-commuting variables 132, 22 skew 1, then I'm going to let this permutation act on, well, my source Schur function S22 skew 1, which is this thing right here. And what does 132 do? Well, it just swaps 2 and 3. Okay, well, if I just swap 2 and 3 here in my index, nothing happens. If I swap 2 and 3 right here, nothing happens. And so I just get back a half h123 minus a sixth h123. And so now what we're going to do is we're going to generalize our definition of Rosa-Sagan Schur functions to Rosa-Sagan skew-Schur functions in the natural way. What we're going to do is we're going to take those dotted tableau, but instead of them having shape lambda, we're going to have them have shape lambda skew mu. And then from then on, we're just going to do what we did previously. We're going to make the monomials corresponding to it, then we're going to add them all up. So if we do this, then we get the following results. if you take the Rosa-Sagan skew-Schur functions and you let the variables commute, then what you get back is the classical skew-Schur functions along with a coefficient. You also have that our skew-Schur functions in non-commuting variables partition the Rosa-Sagan skew-Schur functions in a natural way. And if you write the Rosa-Sagan skew-Schur functions as a sum of Rosa-Sagan Schur functions, you can do this. And the really amazing thing is, does anyone want to guess? Not Farid or Shushao, they know the answer. What's the thing in your heart? Yes, exactly. Thank you, Jim. It is indeed the Littlewood-Richardson coefficients. So that's the story there. And the really cool thing about a lot of the results to do with the Rosa-Sagan Schur functions is actually to prove the nice partitioning that we had on the previous slide, you actually end up creating a non-commutative Lindstrom-Gesell-Viernot. So that is certainly very cool. And then in my last couple of minutes, what I'm going to do is I'm going to take you briefly into another algebra, that of non-commutative symmetric functions of Gelfand, Krobbe, Lascaux, Leclerc, and Thibon. And it's exactly what you would think it would be. You've just got a bunch of variables that don't commute. You make some monomials, you're good to go. And so what we're going to do is we are going to take the map I, and this is a Bergeron, Reutenau, Rosas, and Zabrocki, but this is not Francois, this is his brother Nontel. And so what this map is going to do is you are going to take monomials in non-commuting variables. And if these monomials have n variables in them, and in particular, you've got that these indices right here are weakly increasing. You take all of those, you add them all up. And then your map is going to send this thing to 1 over n factorial multiplied by our complete homogeneous symmetric functions in non-commuting variables whose index is 1 up to n, just that block. If you have that, then it turns out that the immaculate functions of Berge, Nontel-Bergeron, Saliola, Serrano, and Zabrocki get mapped to our source Schur functions. And similarly, the non-commutative ribbon Schur functions of Gelfand et al. In their original paper that they wrote here get mapped to our ribbon source Schur functions, which is basically just our skew source Schur functions, where you have that this diagram right here is a ribbon. But that is not the end of the story, because there are many open problems. What I've given you is just the tip of the iceberg. We still need to find product rules. What happens when you multiply together two Schur functions in non-commuting variables, or two Rosa-Sagan Schur functions? What's the coproduct for our Schur functions in non-commuting variables? It actually turns out, and this is what I showed with Farid and Shushao, that there's a really beautiful coproduct rule for the Rosa-Sagan Schur functions. It's exactly what you might hope it is. You've got a Rosa-Sagan Schur function, tensor a Rosa-Sagan skew Schur function, along with the coefficient that's a very simple binomial coefficient. Can you generalize our Schur functions in non-commuting variables, for example, to McMahon symmetric functions, or maybe the whole Littlewood functions or the McDonald polynomials that Jim and Anna were talking about, maybe the cylindric ones that Jiangsu Kim were talking about? What's the dual basis to our Schur functions in non-commuting variables? And what's the relationship to the X basis of Nontel-Bergeron, Holweg, Rosas, and Zabrocki, which is also related to representation theory? So with that in mind, that brings to an end my adventures for today. And so my final quote from the Three Musketeers is, "Never fear quarrels, but seek hazardous adventures." And if you want to read more of our adventures, then as I mentioned, the paper has just come out in advances. It's called Schur Functions in Non-Commuting Variables, and it's also available on the archive and from my website. And so all that remains for me to say right now is Kamsahamnida. Thank you very much.
Is there any questions or comments to the speaker?
I have one. Thank you for the nice talk. And when you give a formula for Rose's Sagan Schur functions to some of your new Schur functions, is there a way to divide dotted standard tableau to get one new Schur function? Is it clear?
Right,
Yeah.
so here, yeah, we haven't been able to find it so far. That's a great question.
Okay. Thank you.
Thank you.
So I have one really nice talk.
Thank you.
Do you have a Murnaghan-Nakayama-like rule that would relate your new Schur functions to the non-commutative power sums?
That would be excellent. We do not have one of those yet. We haven't even looked for it yet, right? Farid is nodding. He's like, yeah, we haven't looked for that yet. Another excellent question. Yeah, beautiful open question. We don't have that yet, but great. Yeah, thank you. I should be writing these down. Oh, these are great questions.
Any other questions? If there's no more question, let's thanks to speaker again.
Thank you very much.
So we'll resume at 11. 11 Korea.
Wonderful. Thank you very much.
Thank you. Thank you for the nice talk.
You're welcome. My pleasure.